This is your presenter, Asloob Mudassar, and I am presenting slide number 18F of the course on atomic and molecular physics. In the today's lecture, I shall be covering excited molecular states, Excimer's correlation diagram. This is the sixth lecture of the series on molecular physics. In order to understand this lecture completely, you must go through lecture number 18A, 18B, 18C, 18D, and 18E. And this is the sixth lecture, and some other lectures will also follow this lecture. Excited molecular states. An electron from an occupied orbital of ground state is moved to a higher energy orbital, forming an excited electronic state with energy En of R. E of R for R fixed, that is for a rigid molecule, gives a potential energy curve which converges for R goes to infinity towards the dissociation into separated atoms A plus B star or A star plus B, where B star is the excited atom and A star is also the excited atom. That is the ground state atom plus an excited atom. Potential energy curve for the hydrogen singly ionized molecule are shown on the next page. So you see that E of R is actually the potential energy curve for the molecule in which R is fixed. That is, we are talking about the rigid molecule. And you know that when R goes to infinity, that is when the separation between the atoms will increase. The atoms are separated not only as neutral atoms, but they are separated as one neutral atom plus second atom in the excited state. So the combination that is separated will be A plus B star, where B star stands for the excited B atom, or A star plus B, where A stands for the excited atom A and neutral atom B. So you see that they will separated into a combination of A plus B star or A star plus B. And now the potential curves for the hydrogen singly ionized molecule are shown on the next page. So let me show you the next page very quickly. For example, this is this one. The caption is potential curves for 10 lowest energy states of the hydrogen singly ionized molecular ion. So you see that here in this diagram, I have shown 10 lowest energy states. For example, the state 1sg, 1s sigma g is regarded as 1 sigma g. The state 1s sigma u, simply written as 1 sigma u. The state 2p pi u is regarded as 1 pi u. And you see that I have shown other states, for example, 3d pi g, 4p sigma u, 4f sigma u. And there are also some states, for example, 2p sigma g is regarded as simply 2 sigma g, 2s sigma g will be regarded as 3 sigma g, 2p sigma u will be regarded as 2 sigma u. And then you see that I have another state which is 3s sigma g. So these states are given in the order of, these are the 10 lowest states for the hydrogen singly ionized molecule. And you know that for larger values of R, they seem to converge. For example, in this region, beyond the value of R greater than 4 angstrom, they seem to converge at some lines or at some points, and some other curves also converge along with that. So these are the 10 curves you see, potential energy curves. You can see that in some curves you have a dip in the curves, but there are some curves which don't have the dips. They simply decay. These are the curves which are proportional to the repulsive potential. And if you have a dip, it is called a binding potential, in which the potential has a negative value. The principal quantum number is counted for each symmetry type separately. Lowest sigma u state is numbered as 1 sigma u, lowest pi u state as 1 pi u. All excited states are unstable and dissociates into fragments H ion plus H excited. That is the hydrogen singly ionized ion plus hydrogen in the excited state. Star indicates that the hydrogen atom is in the excited state. So all the excited states are unstable and dissociates into the fragments H ion, H singly H ion plus H star. So from the figure that I have shown, some of these orbital names are given as, for example, 2p sigma g is regarded as simply 2 sigma g. 2p pi u is simply regarded as 1 pi u. Similarly, 1s sigma g as 1 sigma g, 1s sigma u as 1 sigma u, 2s sigma g is 3 sigma g, and 2p sigma u is equal to 2 sigma u. So you see that these are, some of them are of course conventional, that naming, and I have shown, I have kept those conventions over here, and I have shown that what the conventions were used for these orbital names, and I have shown these conventions over here for the few orbitals. The excited states are spatially spread out, and therefore the remaining electron charge distribution between the two proton is too small to compensate for the Coulomb repulsion between the two protons. So you see that there is always a Coulomb repulsion between the two protons, which is overcome by the electrons, by the charge distribution of electrons. And you know that in some excited states, the excited states are spatially spread out, and therefore the remaining electron charge density between the two protons. So you see that here I am talking about the two protons. So the electron charge distribution between the two protons is too small to compensate for the Coulomb repulsion between the two protons. So you see that here I have shown 10 lowest energy states for the hydrogen molecular ion, and from the lowest, for example, this red one, which is 1s sigma g, or simply 1 sigma g, is the lowest in energy. And then you can see that the other orbits which are lying relatively higher in energy with respect to the previous one. For molecules with more electrons, there are generally many bound excited states. So if there are more electrons in a molecule, then generally there would be many bound excited states. Potential curves of the lithium diatomic molecule are shown. Doubly excited states are the states where two electrons are excited to higher orbitals. These states dissociate for R goes to infinity. That is when R is very large. In the lithium molecule, the two lithium atoms get separated from each other, or get dissociated from each other into two excited lithium atoms. Core electrons in the 1s atomic shells are barely affected by the excitation of one or more electrons from the outer two s sigma orbitals. So you see that the core 1s atomic orbitals or the shells are barely affected by the excitation of one or more electrons from the outer two s sigma g orbitals. Core electrons do not contribute to the molecular binding. So if there are core electrons very close to the nuclear, very close to the neutrons, very close to the nuclei in a molecule, then of course these core electrons do not contribute much to the molecular binding. If an electron is excited to a state close to ionization limit, molecular Rydberg states are formed. And you know that in the Rydberg states in a molecule, if the molecule is diatomic, one of the atom will remain in the ground state, whereas the other atom is excited to higher excited states, which we here call Rydberg states. The electron is far from the core and does not affect the molecular binding. The potential curves of these Rydberg states are similar to the potential curves of the molecular ions. So you see that here the Rydberg states, since lying very far away from the inner core of the electrons, so we may say that the Rydberg states are similar to the potential curves of the molecular ion, as if the other electron has been removed from the atom. So there is a very similarly between the potential curves of the Rydberg states and the potential curves of the molecular ion. Electrons in the inner shells of two atoms barely contribute to the molecular binding energy. So you see that the inner electrons do not contribute much to the binding of the molecules. They stay concentrated around their nuclei when the molecule is formed. The atomic electrons in the valence shell are rearranged into molecular orbitals covering the volume around the two nuclei. So you see that these are the valence electrons that are responsible for the binding of the electrons, and these valence shells are arranged into nuclear orbitals covering the volume around the two nuclei. The spatial rearrangement leads to a minimization of the total energy at a certain distance Ra, which is called the equilibrium distance between the two nuclei. So you see that when the two atoms are combined to form a molecule, the spatial rearrangement leads to the minimization of the total energy at a certain equilibrium distance Ra between the two nuclei. This is the reason for the binding of two atoms in a stable molecule. So you see that this is the diagram which has been referred over here. For example, in the first paragraph, doubly excited states are the states where two electrons are excited to higher orbitals. And you know that, let me read the first sentence of this paragraph. For molecules with more electrons, there are generally many bound excited states. And the potential curves of the lithium molecule, lithium diatomic molecule, are shown on the next page, which I am going to show you over here. So you can see that these are the excited states corresponding to the lithium molecule, and some of them are doubly excited states. For example, if you look at the curve, for example, over here, the dotted curves, the dotted red curves and the dotted green curves. For a large value of R, that is when R goes to infinity, both converge to the same state, that is 2p plus 2p. So these are referred to as the doubly excited states. So you see that I have shown at the end point where I have shown this vertical black line is the line where I have R goes to infinity. That is when R is very, very large. Then of course this line, vertical line, indicates that here it is the line that gives you R goes to infinity. Now you see that you have some lines, you have some curves. For example, you have 1 sigma g plus curve, then 3 sigma u curve, then 3 pi u curve, then 1 sigma u plus curve, and 1 pi u curve, 3 sigma g plus curve. You see that all these curves, these above curves, the first two curves you know that converge to 2s plus 2s, when R goes to infinity. And one of these two S will be an excited atom, the other will be an ionized atom. Now the other curves, for example, the black curve, the green curve, the blue curve, and the red curve, which have which and all these curves, that will converge to the state which will be in the when R goes to infinity, will be referred to as the two separated particles, two separated atoms, for example 2s and 2p. So you see that there are some other levels, for example pi g and other levels, for example lithium molecule, which is a singly ionized molecule. All these curves, that corresponds to different values. For example, this curve corresponds to 2s plus 4s. Then the black curve corresponds to 2s plus 4p when value of R is infinity. That is when the constituents of the molecules are separated as individual particles. Then you can see that in the green you have 2s plus 5s, and then the red line will converge as 2s plus 5p. And at the topmost I have lithium as 2s, and thus the other lithium, singly ionized lithium, as 1s square. And the term values of these one have been shown as r to the power minus 3 centimeter inverse. And on the horizontal axis, I have plotted the value of R, the separation between the two nuclei, in terms of angstrom, and giving you the values of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 angstrom. And then I have shown the value of R goes to infinity. That is when R is very, very large. Then of course the molecules will split up into separated atoms. So some potential energy curves of the lithium molecules up to the ionization limit, because at the top I have the ionization limit, for example over here, and you can see that the lithium ion is ionized over here. Lithium is singly ionized atom is shown over here. So this is the ionization limit for the lithium atom, for the lithium diatomic molecule. So some potential curves of the lithium diatomic molecule up to the ionization limit, including some doubly excited states shown in the dash curve. So the doubly excited states are also shown over here. And you know that these are the individual separated particles. When R is very large, the molecule will split up into individual atomic particles. For example, 2p, 2p, 2s plus 4s, 2s plus 4p, 2s plus 5s, 2s plus 5p, and so on. Eximers. In the excited helium atom, you know that this star indicates that the helium atom is in the excited state. So in the excited helium atom, the binding energy of the excited electron is of the order of 1/4 of its binding energy in the ground state. And you know that helium has 2 electrons. So I am talking about the excitation of one of these electrons. So I have excited helium atom, and the excited electron in that helium atom has a binding energy of the order of 1/4 the binding energy of that electron when it was in the ground state. This electron can easily be removed from its nucleus and brought into a binding orbital between the two atoms when another atom approaches the excited helium. So you see that if you remove one electron from the excited helium atom, then of course this is excited helium atom which is now ionized, will form a binding orbital between another atom when it approaches the excited helium atom. Helium diatomic, the excited diatomic helium molecule. For example, helium-2 in excited state is shown over here with a star. So the helium excited molecule, which are called dimers, have a potential curve E of R with a minimum. This is true for other noble gases. For example, argon 2, Ar2 excited, xenon 2 in the excited state. These dimers or the mixed excited molecules, for example, argon in the excited state with potassium, argon in the excited state with xenon, argon in the excited state with krypton in the excited state with xenon, etc. These molecules in the excited electronic states have binding potential energy, have binding potential curves, but have repulsive curves in their ground states. That is, these states which I have shown, these excited electronic states which I have shown, these excited states have the repulsive potential when they are in the ground state. But when they bind together to form a molecule, for example, then they have a binding energy which is not repulsive. These are the excited dimers or excimers. Excited. From the excited, I have taken the words EXCI, and from the dimers, I have taken MERS. So excited dimers are called excimers. The potential curves of an excimer is shown on the next page. For example, red is the potential energy curve of the separated atoms that I have shown over here. And you know that this shows a repulsive behavior. But when the molecule is formed, that is the excimer is formed, then you see that in the excimer the potential energy curve has a dip, which means that it is the curve of a binding molecule, whereas the lower one is the curve corresponding to a dissociated molecule. So you see that from the binding molecule you can have a transition to the lower state, and the lower state will quickly disappear. So an inversion, that is a population inversion, is achieved in the upper state, whereas the lower state has no, no binding energy, and the repulsive potential is there. So you can have a continuous region of transitions from the upper binding curve to the lower unbound curve, and then of course a large number of excitations are possible. So two potential curves of an excimer showing the continuous emission spectrum from the upper state to the lower state. The emission is continuous in the form of a continuous band of light. And over here you can see that nu naught actually corresponds to the central curve, central transition is represented by nu naught, and this transition is nu 1, and the other one on the right hand side we have the arrow which represents our transition nu 2. So nu 2 is greater in frequency than nu naught, which is the central one, and nu naught is greater in frequency than the nu 1, which is on the left hand side. So a band of radiations from nu 1 to nu 2 will appear, which peaks at a value of nu naught. So you can see that this is a Gaussian type, roughly Gaussian type curve, and the intensity of the curve is I of nu on the vertical axis and nu on the horizontal axis. So you can have h nu 1 is equal to ei minus e1, where ei is shown over here and e1 is also shown over here. the difference between these two is H nu 1, and the difference between H nu 2 and H nu 2 is equal to the difference between EI and E2. And EI is shown over here. This is EI horizontal curve, and 2 is the curve which is shown over here. So the transition from EI to E2 will give you a frequency nu 2, or the energy H nu 2. So you see that this is the curve of the upper one is the curve of the Excimer. Okay, if a halogen atom with one missing valence electron approaches an excited noble gas atom, the excited electron of the noble gas atom can gain energy if it fills the hole in the valence shell of the halogen atom, forming a molecular ion. This leads to the potential curve E of R with a minimum. That is, when you have a dip in the potential energy curve, it means that this will correspond to the bound molecular state. That is, the molecular state will be a stable state. The fluorescence emitted by these excimers from the levels in the stable energy state represented by EI into the unstable ground state has a broad continuous spectrum. The photon energy h nu, which is equal to EI minus EG of R. This photon energy will have a continuous spectrum. For example, this continuous spectrum has been indicated with its lower limit h nu 1 and upper limit as h nu 2. The photon energy h nu is equal to EI minus EG as a function of R depends on the internuclear distance at which the emission takes place and over the range delta E as a function of R1 minus delta E as a function of R2, where R1 and R2 are two internuclear separations. When the excited molecule vibrates back and forth between R1 and R2. So let me read this paragraph again. The photon energy h nu, which is equal to EI minus EG as a function of R, depends on the internuclear distance at which the emission takes place and over the range delta E of R1 minus delta E of R2. When the excited molecule vibrates back and forth between R1 and R2. So you see that here I am not considering the vibration of the molecule because I am assuming that the molecule is a rigid molecule and the separation between the two nuclei is fixed. But you know that if when the nuclei is fixed, I have the energy which is the energy with a continuous band of energy is given by in the range of h nu 1 to h nu 2. This is a continuous this is a continuous range of energies. So the photon energy h nu is equal to EI minus EG as a function of R depends on the internuclear distance at which the emission takes place and over the range of delta E as a function of R1 minus delta E as a function of R2. When the excited molecule vibrates back and forth between R1 and R2. You know that for a fixed value of R, I have shown you the band of energies between h nu 1 and h nu 2. There is a band of energies at a fixed value of R. And that fixed value of R is in the range from R1 to R2. So in the range of R1 and R2, you can have a continuous range of energies. So the photon energy h nu, which is equal to EI minus EG of R, depends on the internuclear distance at which the emission takes place and over the range delta E as a function of R minus delta E as a function of R2 when the excited molecule vibrates back and forth between R1 and R2. And R1 and R2 are two internuclear separations. So the photon energy h nu, which is equal to EI minus EG of R, depends on the internuclear distance at which the emission takes place and over the range delta E as a function of R minus delta E as a function of R2 when the excited molecule vibrates back and forth between R1 and R2. Eximers are ideal candidates for active laser media. The excited noble gas atoms A star and the halogen atom B collide to produce inversion in the upper state. The inversion is automatically achieved because the lower state is depopulated by dissociation in less than 10 to the power minus 12 second. That is, the lower repulsive state has a very short lifetime. A possible excited scheme is shown over here. For example, xenon plus the electron will form the xenon in the excited state, and again electron with lower energy. So this is the xenon in the excited state colliding with chloride molecule will produce xenon chloride in the excited state plus the chlorine atom. The third one is the xenon in the excited state plus HCl hydrochloric acid. It will produce xenon chloride in the excited state and the hydrogen atom in the atomic state. So you see that these could be the possibilities when there is an interaction between the excited noble gas atom A star and the halogen atom B. Now the correlation diagram. Molecular states can be correlated to the corresponding states at r goes to infinity. That is when the atoms are separated, or which we call SA, separated atoms. So molecular states can be correlated to the corresponding states when r goes to infinity, that is when the atoms are separated, or at r goes to 0, that is when the atoms are united. That is, all electrons form a shell around a nucleus with charge Za plus Zb times E, where Za is the atomic number of nucleus A of atom A, Zb is the atomic number of atom B, and E is the charge on the electron. So this becomes the charge on the nucleus. That is, Za plus Zb times E is the nuclear charge. So let me read again this sentence. Molecular states can be correlated. So you see that any molecular state can be correlated to two different states. One state at r goes to infinity, the other state at r goes to 0. And the state with r goes to infinity means that the two atoms are separated from each other. And when you have r goes to 0, it means that the two atoms have united to form a molecule in which the molecular charge is Za plus Zb times E. Since the symmetry and parity of the electronic states of the system A, B must be independent of the distance r between them, only the selected states of the separated atoms can combine with the molecular states of the given parity and with such states of the excited atoms. So you see that here the point is important, that is the transitions from the molecular state to the separated atoms, and from the separated atoms to the molecular state. Similarly, from the molecular state to the united atoms, these occur when they have the same parity. So AB must be independent of R. Only selected states of the separated atoms can combine with the molecular states of the given parity and with the states of the united atoms. This means that the Gerade states of the united atoms correlate with the Gerade states of the molecules, and the ungerade will correlate with the ungerade states of the molecule. That is, the gerade states of the united atoms correlate with the gerade states of the molecule, and also the ungerade states of the united atoms will correlate with the ungerade state of the molecules. In the figure on the next two pages, energy levels of the united atoms are shown on the left and on the right side of the energies of the separated atoms, where the singly ionized molecule states one of the atoms is always in its ground state. So you see that when we are talking about the excited, for example, singly excited molecules, then in that molecules, one of the atom will remain in the ground state, whereas the other molecule, whereas the other atom in the molecule will be excited. And this is only for the singly excited molecules. Because if you doubly excite a molecule and if the molecule has two electrons, then of course the molecule is completely ionized. And you know that the figure which I am going to show you in the next two pages, you have the energy levels of the united atoms on the left hand side, and on the right hand side you have the energies of the separated atoms. So let me show you those diagrams first. For example, this is the diagram. On the left hand side you have the diagrams of the united atoms. For example, 3s4 3p4 3d 4s4p 4d, and these are the levels, that is 3s sigma 3p sigma 3 pi 3p pi u 3d sigma 3d pi 3d delta 4s sigma 4p sigma 4p pi 4d sigma 3 pi sigma g 4d delta. You know that these are the states that corresponds to the united atoms. And on the right hand side you have the states that corresponds to the separated atoms. Again, the name of the or the labels of the states are the you see that are given over here. For example, 2s 2p 3s 3p 4d 3d and so on. And you know that these are the splittings of these levels. For example, this 3p level in the separated atoms will have 3p, 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 and so on. So one of the lowest energy level will be 3p sigma g. The upper one is 3p pi g. The upper one is 3p pi u, and the top one is 3p sigma u. Similarly, for the 3s as a separate state, atomic state, you have 3s and 3s split into two levels. One is the sigma g 3s, the other is the sigma u 3s. And similarly, we have the separation of these atomic levels on the right hand side as the separated atoms, and on the left hand side we have the united atoms. And you know that I have shown some lines over here, which the correlation diagram, which is called the correlation diagram, and these lines will be explained. For example, the caption of this diagram shows that non-crossing rule states that, here I am talking about non-crossing rule, states that the curve E of R of the same symmetry or parity never cross each other. So on the left hand side and on the right hand side, if you have the energy curves E of R having the same symmetry or the parity, then they will never cross each other. The curve of 1s sigma u can cross the curve of 2s sigma g orbital, but not of the 2s sigma u, because 1s sigma u and 2s sigma u have the same parity, so they will not cross each other. But 1s sigma u can cross 2s sigma g curve or the orbitals, because they have different parities. Similarly, you can see that these are the curves. So on the left hand side you have the united atoms, on the right hand side you have the atomic orbitals. For example, this is 1s atomic orbitals on the right hand side, and this has energies of sigma g 1s and sigma u 1s. Similarly, the 2s orbital will also be separated into two, sigma g 2s and similarly sigma u 2s. And similarly on the left hand side I have the united atoms 1s with a molecular state 1s sigma u 1s sigma 1s sigma, and then you have the 2s molecular state with a molecular nomenclature as 2s sigma. 2p is the state, and corresponding to this state, there are two molecular states, 2p sigma and 2p pi. And again, you see that I have shown the bonding orbitals and the anti-bonding orbitals. And then you see that I have also shown some crossovers with each of these. And the equilibrium distances of these are RE are the equilibrium distances corresponding to these. And you know that at the bottom I have shown hydrogen molecule, lithium molecule, nitrogen N2 and P2. And the caption of this figure is cross correlation diagram of a homonuclear diatomic molecule. On the right side, one of the atoms is always in 1s state to obtain slightly single excited molecular states. In the figure on the next two pages, the energy levels of the united atoms are shown on the left, and on the right side the energy levels of the separated atoms, where for singly excited molecule states, one of the atom is always in its ground state. So you see that I have explained the diagrams a little bit, that in those two diagrams that I have shown, actually this is the same single diagram but split into two parts because it was a bigger diagram. And on the left part of these diagrams indicate the united atoms. And on the right hand side, you have the diagram which represents the separated atoms. So the orbitals in the separated atoms with the corresponding energy levels were shown, and on the left hand side the molecular orbitals were shown, and there were some singly excited molecular states in which one of the atoms is always in its ground state. The correlation diagram combines the corresponding states as a function of R by the curves defined by. So you see that En of R is equal to the integral of phi n star, that is a phi n star as a function of R and capital R, and then the Hamiltonian of the problem, and then phi n of R and capital R, and integration is with respect to d tau. So you see that the correlation diagram combines the corresponding states as a function of R by the curves defined by. So you see that when the correlation diagram combines the corresponding states as a function of R, the curves which combines them is defined by this integral. So let me read the caption given over here. So which are very useful for the correct energy ordering of the molecular states, because the energetic order of the atomic states is not necessarily the same as that of the corresponding molecular states. So the energy levels in a molecular states, that's the different molecular states have energies which are not exactly do not follow exactly the energy of the atomic states. So you see that this diagram, you can see that some lines are quite inclined, connecting the molecular atomic states with the molecular states. And some molecular states are lying higher, and some molecular states are lying lower in relevance to their atomic counterparts. So you can see that there are crossing between the levels, and the levels are crossing, not there are very few of them which have more or less the same level, but in principle they are combining with an inclined lines. So it means that the energy separation between the united atoms and the separated atoms are quite different. So that is what I have stated in this paragraph. So which are very useful for the correct energy ordering of the molecular states, because the energetic order of the atomic states is not necessarily the same as that of the corresponding molecular states. So you see that this correlation diagram will help us on the basis of the atomic states to correlate them with the molecular states. So the molecular states can be perfectly predicted in energy. So let me read this caption. Non-crossing rule states that the curve E of R of the same symmetry or parity never crosses each other. So the lines with the same symmetry or parity will never cross each other. The curve 1s sigma u can cross the curve 2s sigma j orbital, but will not cross the curve 2s sigma u, because 1s sigma u and the 2s sigma u have the same parity, so there will be no crossing between them. So this, you know, that is the non-crossing rule. So with these correlation diagram, you can predict the molecular states, you can predict the energies of the molecular states in relevance with the atomic states, because the atomic states are well defined, and you can correlate the two states together following the crossing and non-crossing rules of the correlation diagram. So this is the second part of the correlation diagram, or you can say it is the lower part of the correlation diagram. And you know that here I have shown the distance r, which is the nuclear separation distance between the two nuclei. And in the united atom, you know that r is very, very small, approaches to 0. And for the separated atomic orbitals, the value of r is very large, nearly infinity. And it will be in between them I have shown the hydrogen molecule, lithium molecule, N2 molecule, and P2 molecule by the dotted vertical curves. So I have also correlated the atomic levels with the bonding molecular states, and the atomic levels with the anti-bonding molecular states have also been shown with the values. And the equilibrium separation distance, the RE, for the different molecules is also shown. So this is the correlation diagram of a molecular, of a homonuclear diatomic molecule. On the right hand side, one on the right hand side, one of the atoms is always in the 1s state to obtain singly excited molecular states. So if you want to obtain the molecular states, that is the singly excited molecular states, one of the atom must be in the ground state, which is the 1s state over here, so that the other state can be excited. The strength of the spin-orbit interaction, for example, generally varies with r due to this coupling order of the angular momenta Li, Si. The total angular momentum capital L is equal to sum over all separated singly or all separated individual angular momenta Li, and the total spin of the system will be equal to the sum of vectorial sum of all the individual spin angular momenta Si. And the splitting of the fine structure components can change from the united atoms to the separated atoms. See figure on the next page. The molecule will not dissociate into neutral atoms, but will dissociate into ion pairs. That is, one will be an ion and the other will, for example, both are ions. One is A plus, the other is A minus, B minus, which means that the species B has absorbed an electron, whereas the atom A or the species A has given off an electron. So let me read the caption of this diagram first. Correlation diagram between a united carbon atom and the VH molecule both of which have 6 electrons. So you see that the carbon molecule and the BH molecule both have 6 electrons, and the correlation diagram is given over here. So first of all, see the united carbon atom or the carbon molecule, C2 molecule. It has 3 states, 3p, 1d and 1s. Okay, this is not the molecule, but this is the single carbon atom. You may consider this as the united carbon atom. So this is a single carbon atom. This is the atomic state of the carbon atom. And in the atomic state of the carbon atom, being having 6 electron, it has 3 levels. For example, 3p level, 1d level, and 1s level. 1s, 1d, 3p. The electronic configuration of the carbon atom is 1s2, 2s2, 2p2. And now I have on the right hand side the BH molecule. In the BH molecule, I have the states. That is, the ground state is 1 sigma plus. The singly excited state contains 3 pi and 1 pi. The doubly excited states, in which the 2 electrons are excited, doubly excited states, has 3 levels, 3 sigma minus, 1 sigma plus, and 1 delta. The BH molecule has the ground state configuration 1s sigma squared, 1s sigma whole squared, 2s sigma whole squared, 2p sigma whole squared. This is the ground state. And if you compute the electronic configuration or the molecular state on the basis of this ground state, you will get 1 sigma plus. The next is that you have singly excited states, in which you have moved one of the electrons from 2p sigma to higher level, which is 2p pi level. So singly excited states are having electronic configuration 1s sigma squared, 2s sigma squared, and then I have 2p sigma and 2p pi, because I have moved one of the electrons from the 2p sigma to 2p pi. So this is singly ionized state. And if you compute the molecular state corresponding to this singly ionized states, which will based on the last two orbital states, will give you two molecular states, 3 pi and 1 pi. 3 pi being lower in energy than with as compared with 1 pi. And then you will have doubly excited states, in which all the 2 electrons from the 2p sigma states has moved to the 2p pi state, 2p pi orbital. So this is the doubly excited states. And the electronic configuration of this one is 1s sigma whole squared, 2s sigma whole squared, and 2p pi whole squared. And here you can see that if you compute the molecular states from the last orbital, which is 2p pi whole squared, then the molecular states will be 3 sigma minus, 1 sigma plus, and 1 delta. So on the left hand side, you have the atomic states from the carbon atom, and on the right hand side, you have the molecular states from the BH molecule in its ground state, in its singly excited state, and in its doubly excited state. And then you know that following the correlation diagram, I have connected them. Correlation diagram between the united carbon atom and the BH molecule, both of which have 6 electrons. So you see that this is the correlation diagram. You can see that how these have been combined. I have given different colors to them. That is the green color, the red color, and the blue color on both sides of the united carbon atom and on the BH molecular side. And you can see that I have combined all the greens have been combined with the green, the red have been combined with the red, and the blue have been combined with blue. And you know that this follows the correlation diagram, the features of which I have discussed before. So the united carbon atoms or the atomic or the atoms in the atomic state can help us to find out the molecular states and to rank the energy levels of those molecular states. If RE, which is the equilibrium separation for different molecular states, are known, the correlation diagram gives the correct energetic order of these states. So you see that in the 2 days lecture, I have explained the correlation diagram. I have talked about a little bit about the excited molecular states, their curves, that is the curve could be repulsive or the curve could be bound curve, representing a dip in those curves. Then I have shown, then I have explained the, that when R goes to infinity, what will happen to these curves and how they converge to their atomic counterparts. This has been explained in this curve. And then I have explained the excimers, how the excimers are formed. And how these excimers could be very useful for laser point of view, giving you a continuous range of energies, because the upper level is a stable level, the lower level is unstable, and the population inversion is achieved in the upper level, and so the transitions will give you the different wavelengths. In principle, a range of wavelengths, a continuous spectrum of wavelengths, and these are some reactions. And then I have explained the correlation diagram, because the correlation diagram connects any molecular state with a state when R goes to infinity, that is when the molecules are separated, and to the state when the molecules, when the two atoms converge together at a distance R goes to infinity, which we refer to as the united atom. So any molecular state can be represented by the state represented by the separated atoms and by the united atoms. This has been explained over here, provided they must have the same, that same parity. This has been explained. And this diagram has also been given over here. And the non-crossing rule has always also given, that is the same parity, never cross each other. And then that this is the second part of the same curve. And then I have explained the correlation diagram with the help of a single carbon atom in the atomic state and the barium hydrogen BH molecule in its ground state and in its first excited state and doubly excited states. These states have been correlated with the atomic states of the carbon atom through the correlation diagram. So you see that this is the end of slide number 18F. So this lecture is not finished yet. There are multiple of, for example, at least 3 or 4 4 lectures on molecular part will also be coming.